Hello everyone, my name is Renke Wang from George Mason University, advised by Dr. Ningshi Yao. Today I'm going to present our recent paper, Robust Model Predictive Control for Networked Control Systems with Timing Perturbations. Timing perturbation usually brings a lot of bad effects to our daily life. For example, in a traffic system, the timing perturbation refers to the inaccurate timing to the expected scheduling. Assume that all the vehicles are following one unified tight schedule, such that they can pass through the intersection smoothly without any congestions. However, if a car arrives at the intersection a little bit later than expected, it will disrupt the flow. Because another car, planning to arrive at the same location at the same time, will get stuck due to the first car's wrong location. And this keeps happening to cause a chain reaction. In this scenario, even a slight timing perturbation from a single car can eventually paralyze the entire traffic system. This will increase the total driving time, subsequently leading to higher fuel consumption and emissions. And this effect will also happen to other scenarios, such as flight delays, which can lead to longer traveling time and a huge amount of extra energy cost. Similarly, the timing perturbation can dramatically degrade the control performance. Here is a simple stabilized control system. The inaccurate timing happened to the control signal can lead to the system state deviate far away from the original trajectory to cause instability. In recent studies on timing perturbations, the focus is primarily on constant perturbations, time-varying perturbations regarded as functions of time, or random perturbations, such as those modeled as Markov chains that obey a certain distribution. However, in reality, the timing perturbation can be purely random without knowing its distribution, which brings us a big challenge in modeling. On the other hand, for recent research handling perturbations with two-based MPC, various types of systems have been discussed. However, the focus is only on the bounded additive perturbation in system dynamics. If we consider the inaccurate timing with two-based MPC approach, it becomes a difficult task, since the asynchronization makes it hard to separate the aerodynamics. So, based on the series above, our research mainly focused on random timing perturbations and solve it by applying two-based MPC approach. Our main contributions are summarized as follows. First, we propose a new two-based MPC with the dynamic controller gain. Second, we establish the system aerodynamics. And last, we obtain the stability condition of the aerodynamics. Let's start with our problem formulation. In the network control system, multiple systems are using one shared resource, and each of the systems has a sequence of tasks to operate, such as data collection, data processing, etc. In this task model, alpha is the task generation time, C is the execution time, and gamma is the task completion time. Because the measurement of the system state is only accessible to the controller at gamma, meaning that gamma will be the control updating time. So in our system model, the control is a piecewise constant signal. For the timing perturbation, we define it as the difference between the actual and the estimated control updating time. Because the previous work has proved that the difference of the actual and estimated task generation time is non-negative and non-increasing. And the task execution time, C, is normally predefined by design. We assume that the random timing perturbation is non-negative and has a finite constant upper bound. To stabilize the perturb system, we first try to use normal MPC. However, since the timing perturbation is a random variable, the actual task completion time will be undetermined. Then the control and state will also be undetermined. So it's impossible to directly solve this. Then our solution is to use two-based MPC to compensate for the random timing perturbation. The main idea of two-based MPC is to design a dynamic feedback control law that compensates for the deviation caused by perturbations. The robust control is the sum of nominal control and the correction term. With this control law, perturbed system trajectory can oscillate around the nominal trajectory and stay within the tube. To distinguish differences in system dynamics, we define the nominal system as the system without timing perturbation. Xn is the nominal system state, and Un is the nominal control, which updates at each estimated task completion time. X is the perturbed state. U is the perturbed control, which updates at each actual task completion time, later than or equal to the nominal control. Our solution has two steps. The first step is to formulate MPC optimization problem only for the nominal system. One thing to note is that the last constraint is to guarantee the existence of the nominal states, where X is the predefined perturbed states constraint, and S is the forward invariant set for the aerodynamics. After proving the forward invariant set is bounded, the difference of these two sets should be non-empty to find feasible solution. The second step is the dynamic state feedback controller design. In the correction term, we propose a dynamic feedback controller gain, which is a function of the timing perturbation. And this is a big difference from the traditional two-based MPC with only a constant gain. This figure is to show that our dynamic control is computable. At the actual task completion time, since we know what is the current time, the nominal state at gamma k is computable. Also because the perturbed state at gamma k is measurable, we can compute the difference between two system states, which is the deviation caused by the timing perturbation. Besides, the dynamic gain is computable because the variables in this formula are known, where the gamma tilde of k plus 1 can be predicted by the timing model from previous work, and gamma is the current time. Then, by applying the dynamic control law to compensate for the deviation, the perturbed system trajectory can oscillate around the nominal trajectory. Our approach has two advantages. First, the perturbed and nominal system states are guaranteed to be equal at each estimated task completion time, and this is proved by lemma 1. This brings us the second advantage. When the timing perturbation begins to be zero, starting from one estimated task completion time, the perturbed system trajectories can immediately converge to the nominal system trajectory and perform the same as the nominal trajectory. The benefit from that is that as time propagates, the task completion time estimation becomes increasingly accurate. Until the timing perturbation approaches zero, the performance of the perturbed system will be almost identical to that of the nominal system. Here we use an example to compare our dynamic law with the traditional two-based MPC. For the traditional method, we compute the constant controller gain for a second-order system. In the simulation, the black solid line is the nominal trajectory designed to track a square wave. For the traditional two-based MPC, the green dashed line is the perturbed trajectory. It's easy to find that there is always a large deviation between the perturbed and nominal states. This is because during some time intervals, such as the time between gamma 7 and gamma 8, the closed-loop system matrix is unstable due to the random timing perturbation. However, with our approach, The red dashed line is the perturb trajectory. It's easy to verify that the perturb and nominal states are equal at each estimated task completion time and bounded at the actual task completion time. Except for this, notice that when the timing perturbation begins to be zero, such as delta 12 is zero, the perturb trajectory performs the same as the nominal trajectory. For the system analysis, our target is to prove that the perturbed system states are bounded to make sure its trajectory stays within the tube as time propagates. To achieve this, in step 1, we derive the aerodynamics by discretizing the perturbed and nominal states, which is presented by lemma 2, where the closed-loop system matrix and the additive disturbance are functions of the timing perturbation. In step 2, we need to prove that there exists a finite four-invariant set for the aerodynamics. First, we prove that the closed-loop system matrix is asymptotically stable through proposition 1 and condition 1, where condition 1 provides the upper bound of timing perturbations to guarantee stability. Then we prove the set constructed by all the additive disturbances is compact through lemma 3. Based on the above conclusion, the four-invariant set can be proven to exist and finite by theorem 1. In our simulation, we have 4 systems with timing perturbations. Then, with the constant gain for the traditional tube-based MPC and the random timing perturbation that satisfies condition 1, we get the trajectories for all systems. The blue dashed line denotes the perturbed system trajectory without any compensation. It is obvious that it deviates from the nominal trajectories. The green and the red dashed lines denote the perturbed trajectory with constant and dynamic gain, respectively. This figure indicates that the green line has a larger deviation, so our approach is better. Especially when the timing perturbation begins to be zero, the red line converges to the nominal trajectory right away and performs the same as the nominal trajectory. Thanks to our sponsor for their support. If you have any questions, please feel free to reach out to us. Thank you.